And helicopter crews rescued an injured hiker who fell on Mount Olympus. Salt Lake County search and rescue crews say the hiker slipped and fell yesterday off the mountain's main trail.
On a cold morning in early March 2025, a team of scientists stood at the foot of Mount Olympus, not the famed Greek peak, but the snow-laced massif of the Pacific Northwest, watching as a laptop brought patterns of colored lines and shifting geometries into focus, revealing data few ever see in raw form. It was an ordinary day above ground, clouds drifting, skiers gliding through valleys, and ice melt furrowing down ancient slopes. Beneath this tranquil scene, however, something extraordinary and potentially consequential had begun. From massive satellites spinning overhead, beams of energy scanned vast swaths of land and water to capture the subsurface picture of this remote mountain. Synthetic aperture radar interferometry, or InSAR, was being deployed at unprecedented precision in North America. For years, the data arrived in fits and starts, faint readings, blips, and anomalies easily dismissed. But now, in 2025's era of deep learning-powered analysis, an unmistakable pattern emerged. Thousands of pixels danced in synchrony, gently warping around Olympus's roots. Their story was both simple and profound. The ground was shifting, unseen by locals and undetectable by traditional instruments. The massif had begun to rise by mere millimeters, yet loaded with geological significance. This was no gradual tectonic drift. It was a silent, measurable shift, hinting at underlying forces and changes with consequences beyond what first meets the eye. What triggered this sudden deformation? Why on Mount Olympus? And why now? As scientific teams synthesized NISAR, NASA, ISRO, synthetic aperture radar, mission data, with updates from the World Magnetic Model, a convergence of clues forced a new set of urgent questions. Was Mount Olympus awakening? Or was this a sign of deeper, less predictable processes? Could this iconic Northwest peak be hiding an undiscovered fault? Or something else entirely? What does it mean when the Earth moves in ways too subtle for our senses, but too significant to ignore once uncovered by technology? Let's delve into the heart of the mystery, where advanced science meets ancient landscape, and every discovery points to deeper unknowns beneath our feet. Beacons in space, shadows on the Earth. The first indication arrived as a burst of raw satellite telemetry, ordinary to most, but alarming in precision to practiced eyes. NASA's NISAR mission, designed to monitor minute changes in landscapes and ice sheets, was uniquely capable of providing coherent InSAR snapshots over regions as remote as the Olympic Mountains. As satellites swept their gaze over the Pacific Northwest each week, they mapped subtle changes, centimeter-sized bulges, faint troughs in the ground. It was the scientific equivalent of spotting a new wrinkle on an ancient surface. By January 2025, these changes unified. Data indicated that the very ground beneath Mount Olympus was lifting more quickly and more broadly than any GPS network in the region had ever detected. NISAR's radar, calibrated with ground reflectors and quantum accelerometers, rendered a startlingly clear image. An oval zone, roughly 6 kilometers across, had begun to bulge, quietly and steadily, with no apparent surface sign for those living in the area. To the untrained, this might seem trivial, but InSAR's power lies in its ability to observe the invisible, to catch what geologists call inflation, the Earth's delicate, often imperceptible breathing. But when this rise accelerates, as observed here, over 14 millimeters within a few months, and when it takes on a distinctive asymmetry, such as the eastern flank heaving upward more rapidly, something well beyond routine is at work. What could drive such a transformation? Was it the swelling of rain-soaked soils, a byproduct of seasonal meltwater, or could the mechanism lie far deeper? Working to verify possibilities, scientists overlaid InSAR with ultra-high-resolution imagery and spectral data, searching for environmental explanations, changes in reflectivity, glacial retreat, or even microfracture networks. Nothing matched. The uplift showed independence from weather, hydrology, and known surface conditions. As the findings circulated, researchers enlisted the latest world magnetic model, known for its critical role in global navigation. WMM 2025 also documented Earth's shifting magnetic North Pole, a multi-year migration from Canada toward Siberia. Curiously, this movement paralleled a growing scientific interest in dynamic Earth systems, including those now manifesting beneath the Olympic Peninsula. So, globally significant satellites and geomagnetic models converged above this place of old growth and ice. Mount Olympus had become, unexpectedly, their focal point. But what, precisely, had shifted within the mountain's depths? The signature of Uplift, decoding the Earth's whisper, while extending InSAR, mapping across the seasons. A narrative began to crystallize from the cascade of satellite data. The Uplift zone was an elongate ellipse, slanting southeast, its orientation tracing nearly invisible faults, remnants of geological events lost to the deep past. Layering digital elevation data over time-lapse scans gave researchers a geological MRI, making visible the movement of the mountain's very bones under unknown pressure. Scientists quickly noticed something unusual. Uplift signatures tend to reveal their source. Magma creates rounded humps, faults yield abrupt, stepped motion, and superficial water drives messy, irregular swelling. But the InSAR data exhibited a unique pulse. Asymmetric, episodic surges in Uplift, out of step with any obvious triggers. Field teams move swiftly, hiking remote folds to lower soil gas samplers and gravimeters into fractured ground. The verdict? There was no surplus water, no anomalous rainfall, no outsized glacial melt to account for the changes. The movement seemed intrinsic to the mountain, a motion not driven by climate, but perhaps by forces deeper and older. Next came the magnetotelluric surveys, studies that mapped the conductivity of rock layers far below the surface. Beneath the uplift zone, researchers detected a conductive anomaly shaped like a vertical plume, suggestive of partial melt or hydrothermal alteration. This was not a conclusive sign of magma, but it echoed what's often seen above slow-forming intrusive bodies. Cryptic magma chamber buried deep within the crust. Carbon dioxide flux measurements added another puzzle piece. In subtle vents and fractures, instruments picked up small but consistent emissions of CO2 enriched in helium-3 isotopes, a chemical tracer typically associated with deep mantle origin. The isotope ratio was not overwhelming, but it was enough to raise alarms. If the gas was rising from deep sources, the region might not be dormant, but rather in the earliest stages of reactivation. Historical seismic records were combed for context. Surprisingly, a pattern of low-frequency earthquakes, long thought to be glacial in origin, began to match the uplift pulses. The revised interpretation suggested that these events weren't surface noise at all, but deep, ductile deformation, a mountain groaning from within. Was this response an echo of far-off tectonic boundaries, or the product of mantle dynamics miles underground? If so, even minute deformation could indicate accumulating stress, energy stored and waiting, sometimes for centuries, before release. As the seasons rolled on and dawn light crept over Olympus's jagged spine, a persistent question haunted research stations and field teams. Was the massif simply flexing under the burden of time, or was this the early stage of a cycle not witnessed in thousands of years? And if so, how much time remains before it speaks again? Mapping Earth's nervous system. With attention growing, agencies, universities, and regional tribal research programs joined in a coordinated campaign. Their shared mission to transform Mount Olympus into one of the world's best instrumented geological sites. In effect, they sought to reveal the mountain's nervous system, mapping subtle internal changes in real time. Technicians installed a mesh of sensors across slopes and valleys. Tilt meters anchored in bedrock captured minute bend. GPS stations synchronized to the millimeter and recalibrated using WMM 2025 tracked slow lateral and vertical movement. Remote magnetometers placed in forests, valleys, and ridgelines listened for magnetic fluctuations and electrical anomalies. Crucially, drones equipped with radar and LiDAR mapped surfaces in ever finer resolution, tracing potential fracture zone and monitoring changes to both natural and human infrastructure. Ground-based soil probes measured for trace gases, especially those like CO2 and hydrogen sulfide, which can indicate pressurized deep processes at work. All this information, transmitted to secure data centers, was pored over by algorithms trained to spot the tiniest anomalies amidst massive data flow. The initial findings revealed the uplift was expanding. New bulges appeared along the massif's southeastern side, overlapping areas known for ancient landslides and long-extinct hot springs. In addition, oscillations, small, repeating flexures in the ground, emerged, pulsing in tandem with the uplift's dominant direction. For the first time, scientists were able to hear, in a manner of speaking, the slow, rhythmic heartbeat of the mountain. Yet it was more than a heartbeat. It was a system in motion. Hydrologists began reporting unusual behavior in the aquifers beneath the region. Springs that had long been dry suddenly trickled back to life. Others turned cloudy with fine sediment, signs of shifting underground pressure and fractured flow paths. Tree ring analysis from forests at various elevations showed synchronized stress events, rapid growth slowdowns that matched recent deformational pulses. Local communities, especially indigenous nations with long-standing relationships to the land, were drawn into the conversation. The unpredictable march of the magnetic north. 2025 did not only bring revelations underground, it was also the year the world magnetic model was overhauled. From military fleets to airliners and smartphone, this model underpins nearly all global navigation. More than just a technical update, WMM 2025 provided unmatched detail, enabling better prediction of Earth's magnetic field shifts, critical for navigation amid ongoing changes. Notably, Earth's magnetic north was confirmed as still moving, a phenomenon shifting it from Canada further toward Siberia, part of a decades-long trend. While researchers caution that magnetism operates on a global scale and surface processes unfold more locally, geophysicists were intrigued by apparent resonance. The direction and shape of recent uplift at Mount Olympus bore a faint resemblance to the arc traced by the pole's migration. With WMM 2025's improved accuracy, all local instruments were recalibrated and referenced to the new model. The enhanced granularity offered by the model, from military deployments to mapping subtle field anomalies, gave scientists confidence that they could detect local magnetic effects if relevant. Ultimately, while no evidence yet points to magnetic drift as a driver of Mount Olympus's activity, the ongoing convergence of geophysical and magnetic science at the site is emblematic of what can be achieved only with global data sets and next-generation technology, tools powerful enough to find signal in the Earth's deepest noise. Echoes from the depths, searching for the pulse. Surface uplift was only part of the story. As InSAR maps outlined an enlarging deformation zone, seismologists deployed rings of sensitive broadband seismometers around the massif. These instruments, capable of detecting microquakes too faint to be felt, aimed to record whatever pulse might accompany the mountain's shifting skin. Within weeks, they identified a new signal. Instead of regular tectonic tremors or sudden, sharp releases, these were low-amplitude, persistent vibrations, a background hum segmented in step with the uplift cycles. Some micro-earthquakes appeared, the stone shifting just enough to generate faint energy bursts. More enigmatic, though, were signals hinting at possible low-level movement of fluids, though nothing definitive. Careful analysis suggested no large influx of magma or pressurized gases rising to shallow levels, but local tremors did correspond with slight surface changes and with periods of lower atmospheric pressure, a complex, balanced system responding to both deep and shallow forces. None of these vibrational events amounted to a seismic crisis, Still, in a mountain not considered an active volcano, their presence was puzzling and warranted further scrutiny. Could Olympus, long assumed dormant, contain slow-moving fluids at depth? Or was this simply a case of the crust responding to transient forces, finally visible because of the unprecedented density of sensors and data analysis? Adding further intrigue were harmonic tremor-like signals, long-duration seismic waves typically associated with fluid movement in volcanic conduits. Although these signals were subtle and didn't match the classic profiles of magma migration, their recurrence during uplift pulses raised eyebrows. Some tremors exhibited frequency gliding, starting low and climbing slightly, like the tuning of a vast subterranean instrument. Deep borehole geophones provided another perspective. Installed thousands of feet beneath the surface, they detected clusters of repeating seismic events, tiny stick-slip motions that often occur when ductile rock interfaces with stiffer crust. These might represent the slow migration of brines, hydrothermal fluids, or gases under pressure, squeezing through narrow fractures widened by uplift. All of this hinted at a highly dynamic, multi-layered system, not a silent mountain, but a slow-moving engine of stress, strain, and fluid migration. While Olympus lacked the dramatic signatures of an awakening volcano, it was undeniably alive in the language of rock and resonance. With each passing week, Olympus offered more data, more questions. It was not erupting, it was not quiet, it was responding. And in the world of geophysics, response is often the first sign that something beneath our feet is preparing to change. Lines in stone, clues in the mineral record. Fascinated by mounting evidence of change, geologists turned to core samples from the uplift zone, drilling deep for fresh mineralogical clues. Cores reaching hundreds of meters below the affected area revealed new information. Mineral layers displayed evidence of hydrothermal alteration, from changed feldspar to new accumulations of zeolite. Some layers trace the mountain's geologic past, volcanic glass trapped with rare isotopes, zones of altered minerals such as perlite and smectite, and localized enrichments in lithium or boron, all signs that hydrothermal fluids had once, or perhaps still, moved through these rocks. Of special interest were the uppermost layers, where mineral changes were recent or even ongoing. Shifts in clay structures, rapid illitization, and subtle crystalline realignment indicate active heat and pressure, suggesting thermal or fluid pulse at depth. The uncharted territory of forecasting. Harnessing supercomputers, teams integrated InSAR uplift data, GPS records, seismic readings, mineral shifts, and even the new magnetic field projections. AI models tested thousands of scenarios, looking for signatures that had preceded geological hazards in other parts of the world. The result was sobering, a complex spectrum of futures, mostly benign, predicting a modest resettling of strained crust. But a small percentage forecast more severe outcomes, accelerated uplift, sudden slips on hidden faults, or, in the rarest cases, formation of fractures that could trigger landslides or persistent ground deformation. While there was little evidence of magma ascent or imminent volcanic eruption, even mundane geological events in this region, home to vital ecosystems and communities, could have far-reaching consequences. Mount Olympus, quiet for millennia, now existed in a state of dynamic sensitivity. The world watches, the Earth waits. So what does this mean for life in the Olympic Peninsula? In 2025, there have been no catastrophic events, no new fissures, no plumes, no eruptions. Still, this is a story of potential, not disaster, of a planet whose mysteries are increasingly measurable but remain only partly understood. The new generation of InSAR maps, validated by NISAR and ground sensors, provides a level of oversight unimagined a generation ago. But their clarity also reveals how little we control beneath our feet. The alignment of subtle uplift with unexplained signal, the ongoing drift of magnetic north, the mineral record alive with hints of change. For now, the story is one of vigilance. Researchers continue to monitor, models get refined, and communities are briefed. All await the next data point, the next whisper from the Earth. If you're captivated by this unfolding investigation and want to follow along as new signals emerge, join us, share your thoughts, and help us decode what these shifts might mean for the Northwest. Thank you for watching. Keep your eyes not just on the peaks, but on the horizon. The world is shifting, and now, more than ever, we have a chance to listen.